Here we have a particle with a mass of 7.8 kilograms. It is not actually moving in the xy plane, but rather it's moving with some velocity with x and y and z components, so someplace in space, and it's at some location in space, and we want to find the angular momentum about the origin in this case. So if we're looking for angular momentum, we know how to do that. We know how to find the angular momentum. It is r cross with p. Here, p is the linear momentum. So it's m times v is p. For the sake of simplicity, because we have a bunch of decimals here, instead of multiplying m and v to find p at the beginning, what I can do is I can factor out that m. Since it's a scalar, it's just a number. And I'm going to go ahead and find the cross product of r cross v first. And then I can multiply in m, I can multiply in the mass later to make this a full angular momentum. So I know what my mass is. It's 7.8. And then what I'm going to do is I'm going to multiply that by r. I'm going to cross that with v. Now, what I could do is FOIL this out, essentially, and look at the cross product of each pair of terms. I would have 9 terms here, which would be fine. And for each one, I would say I crossed with j would give me k. Right? Counterclockwise is going to be our positive direction. And then if we go j cross I would give us negative k, because this would be going back clockwise. That's our negative direction. That would be one way I could do this. It's a way that you should know how to do, but it can also be kind of tedious. So I'm also going to do the matrix method, where I'm going to take I hat, j hat, and k hat, and I'm going to take the components corresponding to those unit vectors from the position in the middle and from the velocity in the bottom row. And I can take the determinant of this matrix. So technically, take the determinant of this matrix. And what I've done here is looking at the I component, I take these two multiplied minus those two multiplied, and that gives me the I component. Looking at the j component, I take these two multiplied, and I subtract these two multiplied, but j has a negative factor out front of the whole thing. And then looking at the k component, it's these two multiplied minus those two multiplied. And so I can simplify each one of those. This is really r cross v. I still need to multiply the 7.8 times the whole thing, because the 7.8 is the mass. And so I'm just going to distribute that mass to each term as well. And here I have the angular momentum of this arbitrary particle with an arbitrary speed moving in an arbitrary direction, someplace in the 3D space around the origin. You could think of this as the x component of the angular momentum, the y component of the angular momentum, and the z component, depending on what axis you are rotating about. If we wanted to find the magnitude of the angular momentum, in this case where you have 3 components, we're basically using Pythagorean theorem, but we're looking at it in 3 dimensions. And when we multiply all this out, we get 432 kilogram meters squared per second would be the magnitude of the angular momentum, which we find by combining the components of the overall angular momentum vector.